Hello, welcome to the first video on designing data intensive applications, more commonly known as high level designing of our system. I'm going to use Martin Kleppmann book as the base for all the lectures that will follow, including this one. Apart from that, the other resources that I have found over the internet while I was going through the concept myself. And the main motive is to reduce the time and effort it will take you to grasp the concept. So hopefully it would be useful for you. And this to go through these videos you don't need any programming language knowledge beforehand. If you just, it would help if you know some SQL commands, if you have some experience in application development. You will be able to understand the concept, or you will be able to relate to the concept easily, but that is not a very strong requirement here. You can just go through these lectures, and I will also share the book detail in the description section, which you can use to explore it more further. And yeah, basically let's jump into the first lecture. Just a small disclaimer that this is going to be a on a little boring side because it deals with a lot of terminologies, but please bear with me because these terms will appear again and again in the lectures that will follow, and it will be used as a building block for all the concepts that we are going to look into. So let's jump into the next first chapter itself, which talks about making an application which is reliable, scalable, and maintainable. What it means, it will come in the following slides, and all I will also share these slides in the description section, so that you can use it to revise it or to use in any way you want to. So any application that we develop or we see around, it can broadly be classified into two categories. It could be compute or data intensive applications. As the name suggests, for data intensive application, it is more concerned about the data. It has a large amount of data that we want to store, that we want to process, and when the user asks for it, retrieve those data and show it to the user. Some examples can be some streaming platforms like Netflix and Amazon Prime. They are data intensive applications that they have large amount of data in form of movies, TV series, documentaries, which the user can retrieve whenever they want to see something. And any social media platforms such as Facebook, X, they're all data intensive application which has a lot of information about the user, and when the user asks for it, the social media platform, whether it is Facebook or any other, they provide those data to the user. Other than data intensive, the compute intensive applications are those which is more related to computation, where computation is more complex. It is of more uh, significance. An example could be, let's say you develop an app which takes an integer from the user and then calculates the factorial of that integer. The integer could be anything, like the user, let's say, wants to calculate the factorial of 1 million. As you can see, there is no more there's not much data storage needed here, but mostly computation needs to be done. A lot of complex computation needs to be done to serve the user, or the user can ask for something else. Like we can have an app where we input an integer from the user and figure out what is the nth prime number. So user, let's say, inputted 1000, we will figure out what is the thousandth prime number. This also involves a lot of computation, not much of data. So in this lecture and the lecture that will follow, we are mostly concerned with the data intensive application where we are handling large amount of data instead of compute intensive application, which is a whole different domain in itself, which we can deal with it later in a different series. But for this series, we are mostly concerned with the data intensive applications. For any data intensive applications, there are certain guarantees or certain functionalities that the user expect. Let's take off another example of a data intensive application. Let's say you have created a app called Photos. So you allow the users to share their photos in your app, and later when they want to check them, they would be able to retrieve it from your application. To serve that, you need a database, so that the user, once they store their photos in your application, it gets stored into your database, and they can be very sure that once they have saved it in your application, later when they want to retrieve it, they would be able to get to see those photos. Similar to database, we also have a concept of cache. So there can be some photos that the user want to share or to save, which they more frequently retrieve as well. It could be photos related to some ceremonies, some birthdays, or some special occasions that they frequently check out. We can keep those photos in some cache, which is present in memory, and the retrieval of it would be a lot quicker. Instead of storing them in the database, we can store a copy of them in the cache, and when the user wants it, we can just retrieve it from the cache and show it to the user. Apart from cache, we also can have search indexes. Search indexes, let's say, it is more like a lookup which help user to find some data in a database rather quickly. In our example, you can say that if the user wants to see all the photos that he has saved in some month of the year, he would be able to make a query for it. He can say, show me all the photos that I had saved in July 2023. And using the lookup, we can quickly find out all the photos that was saved in that month of the year and show it to the user. Without the search indexes, it would be very painful for the user if he has a lot of data to scroll through all the photos till he gets to that intentional intended month and the year. Apart from search indexes, we also can have stream processing. Stream processing is the runtime analysis of all the data that we get in our application. Let's say in our example, a user saved some photos and later he tries to save another photo which is already present in our application. So we can say that to the user that, okay, you have already saved this photo. Do you want me to share a copy of it, or do you want me to ignore it? We can use a stream processing in those cases. Similar to, or rather dissimilar to stream processing, we have batch processing, which is not runtime, but it is mostly an offline job, where we can get all the data that the user has, in our case, all the photos that the user have. And based on some analysis, we can create, as you must have seen in Google Photos, they create what is called memories. It's a slideshow of all the photos which Google think is of relevance. All these things can be done as an offline job, as a batch processing job, using all the data that the user has provided. So from application point of view, we it is not necessary that you need all these functionalities in your applications, but it is a good to have. Once you understand the concept of what is a database, what is a search index, you can decide on yourself whether you need it for your application or not, and if you don't have it, whether you will need it later in the future. And apart from that, you also need to understand, I mean, we have covered it in different chapters. I have covered it in different chapters, upcoming chapters. The reason being, all of these are of much importance. Like the database that you are choosing can be very specific to your solution. If it database can be a relational database, or it can be a NoSQL database. Based on your application, your requirement, you can decide which database to go for, which suits your need the most. A similar thing can be done for stream indexes as well. You can decide on which search indexes help you the most for your scenarios. So that is the reason I have covered all these different functionalities that you see here in 5 different chapters, a chapter dedicated for each of them, which we will cover in upcoming weeks. But for now, you just need to understand what are the different functionalities which is expected from a data intensive application. Now that we have covered different functionalities of data intensive applications, let's look at different aspects which is expected from such application. They are broadly classified as reliability, scalability, and maintainability. We will just dive into what these terms mean and why are they Why are they of importance for any application to be successful? Reliability simply means that the system should continue to work as expected by the user, even when things go wrong. And there are hundreds of things that can go wrong in a system. Uh, let's look at some examples or such cases which can go wrong. So, when the user in our example has stored some photo, he wants to retrieve it later, and he should be able to retrieve it no matter what happens for our system to be reliable. That the user can rely on our system that whenever I saved some photo and later when I want to retrieve it, I would be able to retrieve them. Similarly, he can be user can be very sure that whatever I have saved in my application in our application, it is not prone to any unauthorized access. Like say you are sharing some or you are saving some personal photos, and you don't really expect any unauthorized access to those databases, so that your privacy could be compromised. And similar to that, the system should be reliable in a way that even when the user gives an incorrect input, uh, the system shouldn't crash. Like it should be able to tolerate, you can say, it should be able to tolerate incorrect input provided by the user. In my previous example, when we were discussing about search indexes, I said users should be able to search via month or year. So what if the user makes a query, show me photos from next year? Let's say it is 2024 and he says, show me photos from July 2025. So there are no photos which were actually saved in that day. So that is a problem with the user input, but we can't really control what the user is going to input. So we need to make our system that we have developed to be tolerant to such faults. The faults could be anything. User provided input could be invalid, or the database that we are using to store all the photos, it can get corrupted, or the data center where we have kept all the database, it has suffered a power blackout and is not able to serve any purpose or serve any request from the user. So all these are faults which can occur in any system, and our goal is to make our system as fault tolerant as possible. Meaning, when we expect the fault to happen, and what we can do to make our system tolerable to those faults, so that even when something goes wrong, our system continues to work decently well. We cannot guarantee 100% fault tolerant system, as we will see later, but we can guarantee but we can give our best, we can try our best to make our system as fault tolerant as possible. Meaning to say, we can try to make our system as reliable as possible. So what this fault that I keep talking about, what are these faults that can occur, right? So in our example, let's say if I keep all the photos in a hard disk and hard disk crash, and I say, okay, I can't, when the user asks for those photo, I can't give those photo to the user because hard disk has already crashed and or it has got corrupted and not able to serve the user. So this is one example of a fault that can occur. That the place where I'm storing the all the details, all the files, all the photos, it can get corrupted and I may not be able to serve the user. So what we can do is we can add redundancy. We can make multiple copies of those photos. Instead of having one hard disk, we can have 10 hard disk. And we say that when the user save some photo, we won't just save it in one hard disk, but we will save it in other 9 hard disk as well. So that if one crashes, we can still use other 9 to uh, show those photos to the user. So this hard disk is nothing but a hardware, right? So there can be multiple hardware which is involved in our system, and these are what is broadly called hardware faults. So any hardware that we have used in our system uh, can go faulty, can not give expected result, and in those cases we call them a hardware fault. And the basic technique to solve hardware fault is to add redundancy. As in our case, we added more hard disk so that if one gets faulty, we can still use other hard disk to serve the request of the users. And similar cases in on a similar line, like if let's say I'm using a database to store the all the data of the user, and it is present in one data center. And if that data center has a blackout, it won't be able to serve any request from the user. In those cases, we can have a duplicate data center as well. You can call it a backup data center, which will also have all the data present. And if this first data center is not able to serve the user, we can reroute our request to this backup data center to get to serve the request. And we can also have in this case, like we had a power blackout, so we can have some inverters, some backup chargers, to make sure that our data center continue to work, so that even if there is a power blackout, we can still get to serve the user. So basically the point is to add redundancy. In your case, as a very simple example, instead of going into such complex details, let's say you want to work remotely, or you are attending some class remotely, and you are connected via internet. But what if that power goes out? Like, what if the internet service provider is facing some issue and is not able to serve your request? So as a backup, you can have another ISP provider, another set of router that you can then switch to in case the first one fails. So this is a sort of redundancy that you add to make sure that when you are attending your online class or when you are working remotely, if one system failed, you can switch to another system. Or if you have one laptop which you are using for work, if that laptop is not working correctly, you can have a backup laptop which you can then use to complete your work. So basically that is the concept of redundancy that we have, that we use in our data design when we are dealing with hardware faults. So if any hardware device that is prone to failure, which is actually the case in almost with any hardware device, that it is prone to failure. So if we know that it is prone to failure, we can always have a backup devices, that if the first one goes wrong, we can use the data or detail from the second one, or we can use the second hardware to serve the same purpose which was supposed to be done from the first hardware which has gone faulty. So that is one thing which can go wrong in our system. And by by using the concept of redundancy, it basically making use of duplicacy, we can make our system more reliable, that it will be able to serve the purpose of the user even if something goes wrong underneath. Other than hardware fault, which we just saw, which can be solved using redundancy to some extent, we also can have software fault. Software fault are more unlikely to be predicted, and it lies in the system for a long period of time, and it based on some input and based on some conditions, they start to error out. In example, you can say that you are using, let's say you have an app which shows how many days are remaining in your birthday, right? You can ask how many days till my birthday, and it gives you number of days for that. And let's say the user's date of birth is on 7th March, and if he makes a query on 24th Feb, when is my how many days till my birthday, it gives a correct result. But if we have not considered the fact that there could be a leap year in between, the user may start getting incorrect result. Uh, uh, in our case, when the user makes a query on 24th Feb, he will get to say that your birthday is in 11 day, but in reality the uh, actual day is 12. So that makes the system less reliable in a way that the user now cannot rely on this app to figure out how many days are left in his birthday. This is a very naive example, but there was one error that occurred due to this leap second fault in Linux kernel in back in 2012, where all the processes in the system they leaped 1 second, and because of that leap of 1 second, they figured out that most of the applications are which are in sleeping state, they should be running, and all the systems application started running, kernel system applications started running at the same time, freezing the CPU, and led to the downtime of many of popular websites like Reddit, and even affected Amazon Web Service. So Software faults are not very easy to be predicted, but they can be these faults can be tolerable in a way that you can think of different corner cases that can happen by proper monitoring. You can see when the success rate is going down, you can determine what is going wrong and make the system changes to make sure that the fault doesn't affect many user and it becomes more tolerable. So hardware faults are is still easy to predict, that you know that something is going to go wrong and you have a foolproof plan of using redundancy to address it. But software fault can occur as a complete surprise, and each software fault is of different nature, and to fix them it needs different approaches, and it can come with a lot of experimentation, lot of thinking, and that way you can make your software you can make your application software fault tolerable as much as possible, but it would need a lot of careful thinking and analysis. Basically, software fault can also happen like when you say you have a payment system, like you are, let's say you let the user purchase something and make the payment, and the payment gateway, there's some problem with the payment gateway itself, that you depend on some third party, and that license has expired for your application to use the third party application. So in those cases, the user won't be able to make any purchases, and your system won't be working as intended, meaning to say it won't be reliable just because something has failed underneath. So all these things would need a lot of consideration, a lot of attention from the uh, developer point of view to understand what can go wrong, and thinking ahead of it, fixing it, and providing a solution for it. So those are software faults which are very undeterministic in nature and can happen anytime. And yeah, as I said, since there are different categories of software faults that can occur, there are different approaches on how to fix them and to make and to make our system reliable. And the one such solution is to have as much testing as possible, to have as good monitoring as possible, to make sure once in the monitor you see that in the telemetry you see something going wrong, you can identify the error which is leading to these failures and then go ahead and fix it to minimize the software faults that can occur in the system. Similar to software fault, the major problem comes from the human error itself. Human error can be anything, like from a bad code change deployment to a data server which is serving all the requests of the user, and someone just unplugs the power to the complete data center by mistake. And it is not something very unheard of, and it can happen all the time. So as in the case of a bad code deployment, we can provide use developers with a complete sandbox environment where we can experiment with real-time data to see how the system will behave before deploying some changes. And again, we can also have like thorough testing of whatever the code changes, let's say the user is making in our application. It is tested thoroughly. It can be tested using unit test or integration test, live production tests which makes a test query on a frequent basis to our application to see how the system is behaving. And if something goes wrong, it should notify us that the system is not performing at a reliable rate, at a good success rate, and something needs to be checked, something needs to be corrected, and something needs to be fixed. So similar to software fault, with human errors as well, we can uh, we can think of different scenarios which can lead to such failures. We can experiment with different data, we can analyze, we can monitor, just to make sure, if something goes wrong, we can quickly identify the root of the problem, fix it, and then resolve the issue, thereby making the system fault tolerable to human errors as well. In our cases, like if the user has if the developer has pushed some incorrect code, we should have a mechanism to roll out a fix for them quickly, or revert the changes that led to all those failures quickly, so that least number of users get affected by such changes. So yeah, basically, by using all these analysis and by monitoring and thinking of thinking of corner cases, analyzing the different situations that can happen, we can minimize such software faults and human error faults to make our system as reliable as possible. As I'm saying, our system can be fault tolerant and it cannot 100%. Uh, we cannot say that there won't be any fault, because as you can see, there are a lot of things involved which can go wrong, from hardware to a very small mistake from the developer, uh, from the people who are maintaining the data center. Anything and everything can go wrong, and the idea is to make sure that we can minimize such fault as much as possible to make our system as reliable as possible for the user. More reliable this our application is, the more it would be used by the user, it would be more trusted by the user. So that makes reliability a very um, important aspect of any applications that we develop. Two quick questions just to make sure you have understood the concept of reliability, and one term that I used about the test, unit test and integration test. What is the difference in the concept of these two, or if you are familiar with the concepts or not? If required, I can reply in the comment section to make you understand better. Another important aspect of any data-driven application, data-intensive application, is scalability. In our example of a photo app, let's say it is working perfectly fine for 100 users. There are 100 users who are saving their photos in a day. But what if your app becomes a hit and now there are 1 million users using it on a daily basis? So what is the guarantee that the application which was working perfectly for 100 users, it will continue to work nicely for 1 million users as well? This is what is covered as part of scalability, which says that if the load increases, I will come to this term load. If the load increases on your application, how does the performance of the system degrades or remains the same? The load could be anything. Like in our case, we are storing the photos in our database, like we are making write request to our database, or it could be retrieval request from the user. So number of requests that we get from the user to get some photo, that will also increase with the number of users that we have. And instead of 100 users, now we have 1 million users. So roughly speaking, the number of requests to get the photos will also increase by 10,000 times. So if that happens, whether our system is still performing well, or if it is crashing, or if it is not able to um, serve the request of the user, this is all covered as part of scalability. Let's consider Twitter as an example to understand scalability. So in initial days when Twitter started, it didn't have many users, and it used to have a simple architecture as shown in the first diagram, where whenever user posted a tweet, it used to update the tweets table that you see in the middle, where it will have the ID of the tweet, the sender ID, the guy who posted the tweet, what was in the tweet as part of the text, and at what time the tweet was made. And when this was done for every posting of tweet, whenever a tweet was posted, this tweets table was updated. And later when another user logs in, we used to and there was a request to see the home feed. Twitter used to see all the followers, all the people this user was following, meaning to say it used to check the followee ID of the logged in user, and it used to go to the tweet table again and see if there is any tweets related to this followee ID, and if there were any, it used to collect all such tweets sorted by time, created time, and show it to the logged in user in its home page. Later, Twitter realized, like, as you can see, posting tweet was fairly simple. It just used to update the tweets table and be done with it. But when reading the home timeline, when the logged in user is checking his own timeline, it used to do multiple things. It used to go through all the follow ID of the currently logged in user. Used to go to the tweet table to see if there are any tweets from such follow ID. If there were any, it used to collect all the tweets, sort it, and then show it to the logged in user. So it was doing a lot more work during the read part, during the home timeline reading part, compared to posting of tweet itself. Later, when Twitter started to get more user, it started to get more data. It realized that the number of tweets requests, it used to peak at some 12,000 requests per second. But the home timeline request, which is a read request to read all the tweets from the followee, it used to be some 300,000 requests per second. Meaning, it showed that the number of tweets uh, which were happening were less than the number of read requests which were happening. So it made kind of sense to, earlier, as you saw, that we were doing more of operation during the read part, compared to the write part, which is of the posting tweet. So Twitter, using this, understanding this is rise in scale, suggested that we should use a different approach, that most of the work should now be done during the posting of tweet itself, instead of reading of home timeline. Meaning to say, it should do more work during the write request itself instead of read request. What it started to do was, whenever the user posted some tweet, it created a sort of a mailbox for all the followers of this user, of the person who is making the tweet. And the moment he tweeted something, all those tweets used to get accumulated in a queue of these uh, followers. They all have a sort of a mailbox, you can say. It used to get stored in a queue, and when the follower gets online and he wants to check its home timeline, it just used to make a get call, and it used to get all the tweets that was already made by the user. So now more work is now being done during the posting time, compared to reading time. That is, more work is now done at the write request compared to the read request. The reason Twitter made this change was because it realized, with the increase in number of users, increase in number of tweets, there are more read requests compared to the write request. So it made sense to minimize the number of work, minimize the number of operation for the read request, to minimize the response time for the read request, to have a better response time overall. As you saw in the previous example, once the number of tweets started to increase, Twitter made a change in its approach in how operations are done at tweet posting time, and when how it is done during the reading of the home timeline. You can see that if the Twitter has not made this change in approach, the response time would have been very high. Reason being, the more frequent operation was taking a lot more time compared to less frequent operation, which was taking rather less time. So it adjusted the behavior of the application in a way that more frequent operation is not doing a lot less operation, and thereby taking a lot less time, compared to least frequent less frequent operation. It is allowing it to take more time, and thereby creating an overall response time which is less, in this approach, in second approach, compared to what we had in the approach one. I keep talking about response time. I just wanted to give you a quick understanding of what response time is. So, let's say you are a user, you make a request for something. That request goes to some API. API makes a query to a database. It gets the data and show the response to the user. So the time is spent between the user making the request to getting the response is actually the response time. So in our case of Twitter, you can say the home timeline is the when the user logged in or whenever the user refreshes, how quickly the home timeline publishes for him. That would be the response time for the user. So as in the second approach you saw, the number of operation has gone significantly lesser. The information needed to render the home timeline is already calculated. It's already stored in the mailbox that I was showing you. So it is just a get call to get all the tweets from the mailbox and then show it to the user. So thereby reducing the response time considerably for the get request. So similar to response time, there can be many things when you're this is one performance aspect you can say. The response time in our case it was the response time, but for other it can be something else. So performance is defined by like when you increase some load, be it a request per second or number of writes on the database or number of read requests on the database with the same resources that you have, how much your system degrades, how much the system is affected by such increase in the load parameters. The load parameters can be anything, as I said, depending on your system. It could be number of requests that you get or number of write requests you get or number of read requests you get. It could be anything depending on your system. And if you increase your load parameter, and if you want to continue to have the same performance, if you want to keep the performance unchanged, how much more resources you need to achieve that. So that is basically what is considered in scalability. uh, Simply saying that if you increase the load with the same resources that you have, how much performance degrades, and if you want to keep the same performance and there is an increase in the load, how much more resources you need to maintain the same performance. So both the questions require the performance number. So as I said, one such performance number could be service response time. Simply the time taken from the user making a request to him getting a response will be will be called a response time. And in most cases in of online system, that is what is of importance, that we want to keep the response time to an acceptable limit. In our case of photo app as well, once the user has requested for some photo, he should be able to get those photo in a certain period of time. He shouldn't be kept waiting for minutes to see the photos that he has requested for. So continuing with the response time, like for the same request that the user make, the response can be different. If I say show me photos from last week, it may take some 10 millisecond. If 5 minutes later I make the same request, it may take some 12 millisecond. Meaning to say, since there are a lot of things involved in between, the response time can vary even for the same request. So as one performance parameter, I'm looking at response time. So we say that we will check a mean of the response time it takes for different requests. We will fire hundreds of requests to see what is the response time on an average. But on an average also doesn't give a very clear picture. So we use a percentile. Like if I say the 50th percentile of all the request response time is 5 millisecond, that means that most 50% of my request got served within 5 millisecond, and rest 50% took more than 5 milliseconds. Similarly, companies use different percentiles. So this P50 can be called a median response time, that half of the request served in less than this response time and half of the request took more than the median response time. Many companies use a P90, which is called percentile 90, same as P50, which is for median, percentile 50. We also have percentile 90, which means if the P90 is, let's say, 10 millisecond, it means that 90% of the request got served within 10 milliseconds. Rest 10 percent request took uh, more than 10 milliseconds. Similarly, we can also have, let's say, P95. If P95 is 15 millisecond, it means 95% of the request got served within 15 milliseconds, and 5% request took more than 15 milliseconds. So based on, you can now understand, like if I have a P95 at 15 milliseconds, if my system is scaled to some from 100 users to 1 million user, if the response time remains the same, or if I want to keep the response time the same as it was for 100 user, I can now then decide what more resources I need to continue to have this P95 of 15 milliseconds. So this is how, excuse me, this is how you measure the performance, and you determine if my system is going to grow, if it is going, uh, if it is scalable, then what is the resources that I need to have to make sure the system continue to perform the same way as it was performing with a lesser number. So it can be that I need more CPU, I need more databases, I need more network bandwidth. Using these numbers, I can determine what more resources I need, and until and unless I reach the expected performance number, I can keep on increasing the resources with the increase in the load that we get on the system. So that is the basic concept of scalability. It just means that once the load on your system increases, this load could be anything from request per second to anything involved in your system, like writing to the database, reading from the database, or updating your database, and server serving some request from the client. All these things can be called a load, and once this load increases, how your system behaves. If it doesn't behave well, you can determine some performance on which you want to uh, define that the system is behaving well or not. In our case, it was response time. Based on response time, I saw, okay, if I keep on increasing the load, the system performance goes down, and if I want to keep the performance good enough or at the same stage, I need to add some more resources to it. And that's how we determine if the system is scaling well or not. And if it is, then it's fine. Otherwise, we can add resources. To make the system scalable, we can have, like in our photos app, like we are writing to the database, right? We can we have a concept of called scaling. In scalability, to address scalability, we use scaling as the solution. It can be vertical scaling or horizontal scaling. Now let's say in your photo app you had some 100 GB of data, and each user on average stores 1 GB of photos. Now that you have 1 million user, you will need 1 million GB of data. So since you had just 100 GB of database, it won't be able to cater to all those 1 million user. Now that you need to scale up, so you can scale by adding a database which has high capacity, like 1 billion GB capacity, 1000 TB capacity, or you can have 1 million database each of 1 GB size. So the first approach is called uh, vertical scaling, where you are not increasing the node, but you are increasing the capacity of the node itself. It's just one node, just one database, but you are increasing the capacity of it, and that is called vertical scaling. And the horizontal scaling is you are keeping the same size, but you are increasing the number of nodes itself. Instead of having one database of 100 GB, now you are having um, a million, or rather a million database of 100 GB, 100 GB each. So those two approaches can be used to address the scaling. It I showed an example of database. It can be used for CPU, it can be used for network bandwidth as well, that you increase the network bandwidth of the existing system, or you can have multiple connections to address this scalability issue. So yeah, those two approaches are used. It could be vertical or it could be horizontal scaling, and there is one more concept called elastic scaling, which it keeps on using the vertical scaling until it reaches some threshold, and then it decides, no, I need some more resources, so it adds one more resources to it. And as long as it is needed, it will continue to expand in the horizontal approach. And once it thinks that it doesn't need some resources, it can just it starts removing it from the system itself. So elastic approach is something complex, which we will cover when we are talking about different solution to scalability. But for now, you can think of there are three solutions of scalability. First, you have to determine the performance, and performance can be determined. Once the performance is determined, you need to check how the system can continue to behave at a decent performance. For that, you need to add resources, and to add resources, you can either go for horizontal scaling or for vertical scaling or for elastic scaling. Horizontal just means that you add uh, more nodes to the system. In our case, it was database. We kept on adding more and more database till it completely serves 1 million users. Or we can just scale up vertically to have just one node, but it has enough storage to serve all the 1 million users. So that is what scalability means in context of data design. Uh, as I had already explained, that these are the approaches to cope with the increase in load. It could be scaling up, which is vertical scaling, which is to add more and more powerful machine, or to distribute load across multiple smaller machine, which is scaling out or horizontal scaling. And you can also have some elastic system, which is a combination of vertical and horizontal scaling. So you start with a vertical scaling until a threshold is reached. Once that is reached, you start adding more smaller machines to your system, and you keep on adding as the requirement happens. So last concept is maintainability. Now that we have seen how to make our system reliable and scalable, now we will briefly look at maintainability. This is only theoretical, but it is of high importance for any application, because most of the time that we spend as a developer, it is not on building the application but on maintaining it. So that's how maintainability becomes a very important aspect of any any application, especially any data intensive application. So it has some three aspects of smaller aspects of maintainability. It is simplicity, operability, and evolvability. Sorry, I didn't pronounce it correctly, but yeah, simplicity is just mean that for any new engineer who is going to work on your system, he should be able to understand what this system does, that it shouldn't be complex to understand how the system behaves, so it would be easier to maintain for the future. And if there are any bugs, if there are any issues in it, the new engineer should be able to identify it easily, so that so for any application to be maintainable, it should be as simple as possible to make it uh, easy to understand, so that anyone can work upon it. And similar to simplicity is operability, to make the system running smoothly. Basically, if there is a small bug that has occurred, if it is simple enough, if it is well written, the bug can be addressed very quickly, and it can continue to work correctly for as long as needed. Similar to operability is evolvability. Basically, it means if a new feature needs to be added, similar to fixing a bug, if a new feature needs to be added, it should be simple enough to understand how the system works, so that the new engineer or anyone who is working on this legacy system can just go ahead and add the new feature. Or if there is a requirement to move to a different platform, so if the correct current implementation is simple enough, it would be easier to move from one platform to another, to add security patches if needed. Basically, maintainability is all about making the system as abstract as possible to make sure that whoever is maintaining the system in future is not scratching his head, that he understands or she understands the complexity of the of application easily and can keep the system running as smoothly as possible for as long as needed. So this one is a very theoretical um uh, part of this chapter, maintainability. But basically, it just covers simplicity, operability, and evolvability. And yeah, that's all for this chapter. It extended for much more time than I expected. But yep, please go through the slides if you need it, and please comment if you think I missed something or there was some error in it. I will try to address in the comment section as well. And yeah, thanks for your time. See you next weekend.